The following video will be about your odds of having an impactor from space affect you at all. It's 1%. But that isn't the total story. Presumption. The Earth orbiting the Sun at 30 kilometers per second as a basic starting point. That's not its real speed, but that's about right. Impactors have a speed range on impacting the Earth that varies. Their average speed in space is either 40 or 50 kilometers per second, depending on what you're looking for, how dense they are, what angle they come from. They come into specific groups, but it's in that range. If you use it default at 40 kilometers per second and then add 30, you get 70 kilometers per second. And if you subtract 30, you get 10 kilometers per second. And yes, the actual speed range we see for impactors that hit the Earth that we can detect at all is around 10 to 70 kilometers per second. The mean, average, etc. works out to being 2 to 1 speed. Around 11 kilometers per second to 20 is about right. Any object, if you have all the objects assumed to be the same density, diameter, all the other things being the same, a speed change of 2 to 1 means that something coming in twice as fast carries 4 times the energy on impact. And in space, virtually all the objects are in a narrow range of speeds until they hit an atmosphere. It should also be taken as axiomatic that because of the age of the universe and the age of the solar system being almost that age, it's very old, billions of years, and because of the pattern of planets orbiting the sun at anywhere from a year to many years, and a billion years being a much bigger number, most things have averaged out to the following status. We have orbiting heavy objects that don't want to deviate from orbit. Their pattern of behavior, their orbit, is stabilized by how heavy they are and how much that heaviness draws them to stay in check with the sun. Smaller objects are less and less stable the smaller they get, but they too follow these patterns because then they're influenced by being dragged by gravitational pull by the other objects. They also have a habit of following the rule of being in clumps around the sun. The asteroid belt is an example of just a clump of matter, but no planet to drag it there. At least not exactly. Look up orbital dynamics. Now we get to the near-Earth approaching objects that we know about. They are in an orbit. They are in orbits that are predictable. The only thing that can distort them is the moon and the Earth because we don't care about the others. They're orbiting in a way that they come near the Earth. Now, the next thing is, because we have basically an accretion disk-based solar system, most of the matter follows that rule, including the Kuiper or Cooper belt material that's out further and further that mostly follows this disk but gets bigger and bigger, to the point that we get a halo of matter very far out that's still orbiting the sun and still stuck in an orbit, not escaping. The sun so far away means they're moving what we would consider slow by rotation speed, but ridiculously fast by their actual speed. And again, we've gone around the galaxy a couple of times. It's pretty stable. Most things don't want to go outside of this rule. Things from outside the solar system can come in at weird angles like we had over Russia recently, where they come in basically over the sun so nothing was able to track it accurately and hit the Earth. So size matters and speed matters for impact energy, and what it's made out of matters. It's all about matter. We can track virtually anything over a certain size. So those things can be tracked, and the current surveys show us that none of the things that we can easily track, like ridiculously easy, are a threat because we're able to determine that. Things below that size, about a kilometer or around 3,000 feet, it's actually a different number, but I'm not worrying about the details because it's a range and it's kind of a gradient and, there's a sliding scale. Things under a kilometer are harder to track and also, coincidentally, happen to be more likely to be deviated by bigger objects. But then again, what can knock something out of orbit can drag it back into it. Below a certain size and in a size range, what we're worried about is, will it be able to hit and do any damage? Obviously, something the size of a grain of salt isn't going to do anything if the speeds are all about the same. Then again, if it's ridiculously fast, it doesn't matter how heavy it is or how big it is, it's going to hit. It's going to cause some damage. But all near-Earth approaching objects have been tracked if they're a kilometer or bigger, and we know what they're going to do, unless it comes from outside our solar system. The time delay between entering our solar system and being a threat is 7 years. If it's bigger than a kilometer, we can track it. How small does it have to be to escape us to where we get less and less and less information? Let's talk about what's minimum size to do damage. We're going to pick two similar size, very different impactors. 50,000 years ago in Arizona, a 160 foot across iron meteorite, not stony, not ice and snow or methane, iron, much more dense than just stone. 50,000 years ago, it hit Arizona. On impact, it created a almost 4,000 foot across crater, 500 some odd feet, and 150 feet of rim material piled up. It accelerated things to potentially Mach 1 or Mach 2 and pushed things as large as houses or entire city blocks outward to scrape along the ground, not roll, scrape under impact force at 2 times the speed of sound in some cases, and cut the dirt. We have very little evidence, but there is some evidence for that. Distance of blast is unknown because it shredded the area, and then the area weathered over time. We need more recent detonations. These things do not happen often enough for them to be traced. And in some cases, land where it's impossible to trace them, even if they happen and you hear it. I'll be doing that at the end of the video. But what are the components of the impact and energy? Obviously, hitting the Earth creates an energy blast because it hits and displaces material and then transfers the energy to that. Also, on impacting the atmosphere, it breaks up and it turns into thousands of projectiles that hit as well, and also run into the ones that are being thrown out of the hole. At that level, everything should be considered dangerous physical objects. The next thing is the shock wave, the airburst. It doesn't all explode in the airburst. A lot of it does. But that is a source of danger. We'll be discussing an example of just that in a minute. And also, there's one more source that people don't know about. The air pressure directly in front of it, because it's moving so ridiculously fast, it's moving so fast that the air can't compress or decompress or move away, so it becomes compressed into a column of pressure, a ram force. And this acts as another source of concussive energy. Obviously, if it's throwing something the size of a house or the size of a city block at the speed of sound or double that, it's going to travel for a long distance. But these are going to be like spokes of destruction. Between the spokes, where things didn't pass, no destruction or damage will happen. You'll sit there and watch New York be destroyed and your house, but you're not hit with anything. You're just deaf. And that could be 15 miles out, let's say. Now we're going to do a 160-foot ice meteorite. That's the wrong word. I'm using it on purpose to trigger you. 114 years ago, it was an airburst in Russia. It also created a ram force. It made no crater. What was its effect? 16 miles in every direction or more. It took every tree, it either sheared it off, dragged it along the ground, and pushed it into the ground, and then dragged it flat, or it took the tree and slapped it flat and then pushed it downrange. These were old growth forests. Nobody had ever actually trimmed any of this stuff. And this 16-mile diameter circle was hit with something 1/8 or 1/7 as dense. Remember, the speed ratio is 1-to-7 ratio. Just assume the density is 1-to-7 as well. Every time you double the density, you double the impact force. Every time you double the speed, you quadruple the impact energy released, the force that's released. Every time you double the diameter of something, you increase its mass, if it's made out of the same thing, 8 times. It's 8 times as much matter hitting. It's 8 times as worse, even though you only doubled the diameter. And that one, that ice meteorite, was probably going only 11 kilometers per second or 7 miles per second. Again, 1/8 as dense, same diameter. So let's make something 8 times as heavy as an ice block. Let's make it 300 feet across, which would mean it would be 8 times as dense, 8 times as much matter, even an ice block at that point. If you make something 300 feet across, 100 meters, it's called 100 meter equals a crater. It'll always form a crater. It'll always form an impactor. That means it has the explosive force at high altitude from the air burst. They all come with kind of an air burst. And then there's the impactor, and then there's the ram force. So you get 3-for-1 deal here. And that goes 3-for-1 for the impactor being ice. It doesn't matter anymore. It's still going to hit. But it'll have 1/8 the total energy of an impactor that's solid. So let's do our 300-foot impactor, and let's look into how far away it will flatten an entire city to where the city is literally non-recognizable, to where you can't find it anymore. And 10 years later, you won't be able to tell that there was ever a city there, because it'll have also dug up the ground underneath if there are airspaces. 9 miles distant. Nearly the same thing as the one that's half the diameter. Yeah. So what's the minimum range for distance from an impactor? Well, let me explain that next part. This will always also cause an earthquake. It will always cause the ram pressure, air burst, and impactor. It will always cause debris, period, full stop, that comes out at Mach 1 or Mach 2. At this point, it would definitively be at Mach 2, at least for a short distance. And you have a minimum destruction range of about, really, it's 10 miles of dead. These happen every 2,000 years, so what the hell's going on? Why aren't we hearing about this more? Now remember, 100 meter or 100 yards across is the cutoff point where it always will do all 3 forms of impact energy, the energy output. And again, if it's stone, it's not going to be 8 times as dense as the ice. It's only 8 times or so, 7 times really, if it's iron. Stone's in the middle, ice is at 1/8 the intensity of iron. Iron meteorites are the most common. Yes, I used the wrong word there on purpose. 70% of the Earth is ocean, and unless this hits at a coastline and on the shelf. Some coastlines don't have a continental shelf. They just have a drop-off because they're sheared force things. It's not going to create tsunamis. If it hits in the middle of the ocean, you could be at sea on a ship and hear a loud boom with no apparent storm. That might have been one. These happen a whole hell of a lot often than we know about until we started looking for atom bomb blasts and trying to detect people cheating when it came to a nuclear ban, a ban on nuclear testing. Anyway, by 70% of the ocean being there, all things being equal, you have a 30% chance of it hitting Earth. 30% is mostly dry land, but only mostly. Okay, let's go from there. Most of it's not habitable. We exclude Antarctica and Greenland, etc. What's the surface area of the Earth like? Now, these are numbers that I picked up from people who had agendas, so they're going to be a little distorted, so I'm using them to confirm themselves. About 15 or 14% of the surface area of the Earth is modified by humans. That doesn't mean they live there. 12% of the total surface area of the planet is either cropland, rotated cropland, current cropland, or historical cropland. Yes, they had a bunch of qualifications. We're hovering around 10% here. 10% is considered remote because it's more than 2 days ground travel. They don't specify at the World Health Organization if that's by car or by on foot, because they don't care. But 10% of the surface area of the Earth is only, quote unquote, 2 days travel to a city. 10% of the Earth's surface area is inhabited. But again, you'd have to be 16 miles within a blast zone. That's 95% of the people. 3% of it is urban land and cities, which hold the majority of the people that would be hurt if you had a single event. That's why you are going to be having a 1% chance, if you're hit, if the Earth is hit at all, of being within range of giving a damn about it or knowing about it. And again, if it happens in the ocean, it just sounds like a sonic boom and you didn't know you almost got killed. I hope this helps you understand what's going on. I want to point out that only 7% of the population lives in megacity areas and clusters. So your odds are very good. 1% or better. Thanks for watching. Have a good day. Good luck with that.